And first we have Shivam Gola. He's going to be talking about dark matter from particle physics perspective.
Hello everyone. So I will talk on this dark matter from particle physics perspective. Before I begin with, I want to talk on two things because it will be very quick. So what is dark matter first thing? So one line definition to dark matter is that it is not made of proton which makes up everything we know. And second thing, it does not interact with light. That's why probably it called dark matter. And we want to study dark matter from the particle physics perspective. There could be other ways like cosmology or astrophysics, but those things I cannot talk. So yeah, so I will talk on that. So my talk is divided in two parts. So first part is the pedagogical introduction. And introduction part we may ask these kind of question: what is dark matter? What is not dark matter? How to detect for it? And why we believe on it? So these kind of things we will talk on. And second part of talk is little more technical, which is basically one of my work. So I will describe that. So first question is why we believe dark matter. So basically, what are the reason behind we see? So there are, I listed 5 of them. First is rotation curve, second is lensing, third is bullet cluster, fourth is CMB, and fifth is cosmological simulation. These all physics are at very different scales. Galaxy has some scale means size, and clusters has very different scale, and CMB is like universe size scale thing. But the point is, in each scale, we are seeing some anomalies, which is not described by the theories. Theory mean Newton's laws. Okay, so solution to these problems, all these observations, is that either theory has some problem, or either there is some extra matter, some extra stuff is there, which is not like regular matter. Regular matter means made of protons, atoms, or molecules. Those things are not there. So we will go with the second possibility, that there is a extra matter which is required to solve all these problems. There are many evidences, but I just listed 5 of them. So one thing is sure that there is a dark matter. Now, if we know there is a dark matter, what it is. So right side there you see there is a pic, which is basically the standard model of cosmology, which says that there is 5% ordinary matter, mean atoms, molecules, stars, planets, and 25%, which is like 21 here in the pics, is dark matter, which we don't know. It is completely unknown, and the rest is also unknown, which I will not talk on. So there are some properties or some features of dark matter we know, and what are these features? The first thing is it does not interact with light, as I saw. That is why it is not been seen yet. Second thing, it is stable. Stable means it has a lifetime which is infinite, or it has a lifetime which is very large. That is why we are still seeing it today. Okay. Third thing, it is cold. Cold mean it moves very slowly. Slowly mean compare it to speed of light. So okay, so it moves. It moves something like speed of planes, airplanes. Okay, so that is what cold mean. Third observation is the today's number density. Number density mean what is the amount of dark matter today exist in the universe, which is 25%, and mathematically we can write it like this: omega dmh square 0.12, and there could be many others, but these 4 are very strong. Then question is, we identify there is a dark matter, and what are the features of it. So next question is, can we mean like we should identify. Okay, so first proposal was that MACOs, it stands for massive astronomical compact halo objects, and these are actually group of objects called neutron star, dwarf planets, test star, black holes, and collectively people have there are 2 collaboration called MACOs and EUROS. These people have looked up dark matter, looked up these these objects, and they did not find it. So the point is, dark matter is not MACOs clearly. The second thing, if dark matter is not these extended objects, these very large objects, then it should be something we look up in the fundamental particles, atoms, molecule, or nucleus, or maybe beyond that. So beyond that, physics is described by a standard model of particle physics. Okay, so in the right side you see K-pix, which is basically the all the non-fundamental particles that describe the nature. And the point is, none of the particles satisfy the dark matter features. So it should be electrically neutral, it should be stable, and it should be cold. So none of the particles that satisfy None of the standard model particles satisfy those features. So standard model has no dark matter candidate. So if dark matter is not in the standard model, not in the cosmology, mean dark matter, black holes, neutron star, those things are not dark matter, then what it is? So that we will ask, and this thing leads to the something called beyond standard model of physics. Okay, so we will come to it again, and so we had then one last point, how to search for it. So there are three main ideas that has been followed up. It's called direct detection, indirect detection, and collider searches. So what happened? Collider searches, two high energy proton beams collide, and it may happen that dark matter could be produced, and that will be like a missing energy signals that can be seen in the collider experiment. The second experiment called direct detection. What happened in direct detection, that dark matter interact with the protons or detector nuclei, and it may scatter, and it can induce some energy change that can be measured. So that is called direct detection. And third method is a assumption that dark matter have some anti-dark matter, or dark matter may decay, but with very less probability, and it can give you some non-particle like photons or neutrinos that can be detected. So this is the third method of detecting it. And so we will talk on like what is dark matter, what is not dark matter. Now, how to study dark matter? So we should start from the standard model, and the standard model has no particle. So we must go BSM, okay, beyond the standard model physics. So starting with BSM, we should add a particle which represent a dark matter. Representing means it should be electrically neutral, it should be stable, and it should produce the right relic density, and then it should explain this constant like relic density, direct detection, indirect detection experiment. Okay, sorry. So yeah, so one should make a model like that. Okay, and then I move to the part 2. So part 2, this is a model. Okay, so this is one way of looking at it. You see some of the particle on the right side, Q, U, D, N, these are the particles, and there is some extra particle, and chi in the last is the dark matter candidate in my model. Okay, and there is some symmetry group which is basically telling that these particles have some properties. These 1, 2, 3 numbers, these are just telling that these Q, U, D, all these particles having some properties, some features. Okay, and another way of looking that same model in this way, sorry. Yeah, so this is one way of looking at the model. This is another way, writing all the mathematical stuff, allowed terms, and we can compute from these mathematical terms what is called lifetime, decay bits, and probability of some process happening. These things we can calculate from the model. Okay, so first check. So we have wrote a model where dark matter is there. We have added, and so first check we need to see that whether it has no electric charge. First check is already done by the construction. Second thing, we should look for whether it is stable or not. So that is what done is in this plot. There is a colored region you see, and there is a white portion you see. So colored region basically says that basically the disallowed region from theories and experiments on observation or from the model. The white portion is where the model says that there is certain parameter space which is allowed. So basically this comes from the lifetime bound. So what model telling that dark matter is in this white portion is allowed by the lifetime constant. So this is done for certain benchmark which you see, and we can do this analysis again for. So this is U1 model, and I chosen a very generic U1 model. Okay, so generic U1 model mean you can go. There are many types of U1 model, and you can shift to one U1 model to another U1 model just by choosing the right parameter. Okay, so that is what done here, and each U1 model you see some white portion and some colored region. So white portion is the one where the lifetime constant is satisfied. So it's saying that first check is done. Our model has a viable parameter space which satisfies the second property, second requirement of dark matter, that it should be stable. Third thing we should look for after checking that it is electrically neutral, which is by construction in the model. Second thing we should look for the lifetime. Third thing we want to see the relic density, which is mean currently or today the energy density of dark matter today, which is like 25% or 0.12. in mathematical. So these are the results, and you see some colored portion, and some colored curves. So colored curves basically represent the relic density behavior. Relic mean energy density behavior, and colored portions are the constants. Okay, so all those color portions are disallowed region, and the curves which is in the white portion which is actually allowed. So what it's saying that relic density or the energy density which is 25% is satisfied on these color curves when it is in white portion. Okay, so this is done for certain benchmark, certain free parameters of the model, and we did the same analysis for more U1 models. Okay, and you see the more or less same behavior. There is certain white space where where you see red and orange curve which satisfy exactly the relic density thing. Relic density means total energy density. So yeah, so this is done for many U1 models. And then we have seen the relic density. Next thing we should look for the whether model has a feasible parameter space which is allowed by the direct detection bound. So this is what is done here. So you see again the colored region, which is again something called like background things. Okay, so our signal direct detection means you are looking for the particles. Okay, so looking for particle means you're looking for the right signal. Okay, so that signal should be above the background, and the orange region is actually the background. Okay, and you see something called a xenon 110 LZ. These are experimental bounds. These are experimental bounds. So, and you see the red and pink curves. Those are the model predictions. Okay, so you see if your model's prediction lie above the background and below the constraint experiment, it has certain feasible parameter space. So mean it is passing the test of the registration. So this is one way. We have done this for other need to know background as well. And yeah, so in each plot there is slightly this small parameter space which is allowed by the bounds. So that these are auxiliary result, and I think these are not required, but these are okay. Yeah, that's all.